So quantum entanglement and quantum interference, two features of quantum physics. Are they friends or are they enemies? Well, it depends. Here I'm going to show you that there are cases where they actually act against each other. So there's a trade-off between quantum entanglement and quantum interference. In particular, if we have a physical system and we see quantum interference when we run the system through a sequence of interactions, and this system gets entangled with another subsystem that we cannot control. For example, it could be the environment, or it could be another qubit or another system of some sort. So this entanglement will be acting against quantum interference on the system that we have. So here is a very simple example. Let's look at this diagram first. I hope you are familiar with the basic ingredients of this diagram. So you can see that we have two qubits here. They both initially in state 0. The top qubit goes through the sequence of gates, and at first glance it looks like it's a quantum interference, single qubit quantum interference, the golden circuit, Hadamard, phase shift Hadamard. And that's true, except that I have inserted here the control NOT gate. So then you look at this part of the circuit, and you can also see that well, this is familiar because this is how maximally entangled Bell states are generated, right? So it's a Hadamard and control NOT. So it's quite clear that here we will have a state 1 over square root of 2, 0, 0 plus 1, 1. You saw it before. And then the phase gate that acts on the one component of the qubit here. So it should be quite obvious without doing any computation that the state just here is this state. It's 1 over square root of 2, 0, 0 plus EI phi 1, 1. Now, let's see what's going to happen when we run the top qubit through another Hadamard gate. So the Hadamard will be acting only on the first qubit, and so we're going to have 1 over 2, because another 1 over square root of 2, right? So this will go now into a superposition 0 plus 1. So I'm going to have 0, 0, and I'm going to have here 1, 0. So that's what's going to happen to this term. And here I'm going to have EI phi, and I will have one term will be 0, 1 with a plus sign, and I have minus EI phi 1, 1. Well, I can also write this state as follows. So let me just collect all the terms that contain 0. So I'll take this term and this term on the first qubit, and then write this state as 0 plus EI phi 1 divided by 2 plus 1, 0 minus I phi 1 divided by 2. That's just another way of writing this state. Now, the question I'm going to ask is, what is the probability that I'll see 0 here at the output? You can figure this out from looking at this state here. It tells you that there are 4 possible outcomes of this circuit here. They, of course, 0, 0, 0, 1, 1, 0, and 1, 1. And you can see from this state that they are equally likely. Because if you see that take the mod square of the probability amplitude in front of each term, and you will see that they all appear with a probability 1 over 4. So that means that the probability that you see 0 here is the probability that you see 0, 0 at the output plus the probability that you see 0, 1 at the output, so that's going to be equal to half. And of course, the probability that you see 1 is also equal to half. The reason I decided to write this state in this form is just to show you that quite often, if you want to go for sort of a convenient way of calculating those probabilities, we can, if we're interested in probabilities that we see state 0 or state 1 on the first qubit, we write the state in such a way that we have 0 here and some unnormalized state corresponding to the second qubit, and the same here, the state 1 of the first qubit and some corresponding state of the second qubit that doesn't have to be normalized. Now you can normalize this, but if you are interested just in probabilities that you see 0 or you see 1 on the first qubit, it's actually much easier just to take the norm squared of this state here, which happens to be half, and this one is equal to half if you take norm square of this. So that gives you the probability of 0 and 1. So you may think a little bit, it's not an entirely precise kind of a statement, but you may think about this as some kind of a vector coefficient in front of 0. So taking mod square is really taking the norm squared, and that gives you the probability. So that's that's fine. So, but the most important thing here is that now you can see that the probability of seeing 0 or seeing 1 does not depend on the phase phi. So somehow there's no interference. So what happened here? The second qubit got entangled with the first one, right? And another way of thinking about it is you recognize the square root, you recognize the control node as the measurement gate, right? So you may think about the second qubit performing the measurement on the first qubit. So it's trying to learn whether the first qubit in between the two Hadamards is in state 0 or in state 1. And indeed, by getting entangled, it's learning that which of the two cases it is. And so the fact that now it is known to the second qubit which particular path was taken between the two Hadamard gate. Did the first qubit follow 0 path or 1 path? So that essentially destroys the interference. In this case, we have to add probabilities, and the end result is 1/2. It is actually very instructive to think about a situation where this measurement performed by the second qubit is perhaps not perfect. So then you can see how this interference disappears. And in order to see that, it's good to consider this particular circuit. So again, if you look at the top qubit, it is Hadamard phase Hadamard sequence. So we have a quantum interference, and then in between the two Hadamards, there is instead of a control node, there's a controlled unitary. So there's some unitary operation, which is sort of trying to measure whether the first qubit is in state 0 or in state 1 in the following sense. The controlled U means that if the first qubit is in state 0, then we don't do anything to the second qubit, and if the first qubit is in state 1, then we apply this unitary U. So if the first, so that is a kind of measurement in the following sense. The first qubit, if the first qubit is in state 0, then the second qubit will be in state 0. But if the first qubit is in state 1, then you apply unitary U to 0, so you just move, you kind of rotate your state 0, and that's a new state for the second qubit. So the state of the second qubit depends on the state of the first qubit. If it is 0, the second qubit stays in state 0. If it is 1, the second qubit goes into state U acting on 0. Those states do not have to be perpendicular to each other. They don't have to be orthogonal. So you can just move it only just a little bit. So that would be a very gentle measurement. In this case, the qubit, the second qubit, may not have the full knowledge about the state of the first qubit. It will only have the full knowledge where this unitary operation will generate the state that is orthogonal to 0. So let's assume that the scalar product between the two vectors 0 and u acting on 0 is some complex number. I write it as v e2 minus I alpha. I can always parameterize it in this way. Now you can then, well, the special cases, I mean, if our control not case was a special case where 0 and not is x operation, 0 was perpendicular to each other, so that term was 0. And of course, if nothing happens here, if we don't put the control not or controlled u, or suppose we have control identity, which is like identity, then in this case this term is equal to 1. So we know that we already know that if we have this kind of situation where we don't do anything here, if this is identity, say, or we don't put any gate that is trying to measure the first qubit, then we have beautiful interference, right? So the probability here goes like cos of phi. It oscillates with phi. Whereas we know already from this example, if we measure the second qubit, if we put the control not gate there, so the second qubit learns about the value of the first qubit, then this term is equal to 0, and we wipe out completely dependence from phi. But what happens in this particular case? So I will let you do this very instructive exercise. You go through this circuit step by step, and what you'll get at the end, if you calculate the probability of seeing 0 or of seeing 1, you will notice that the interference pattern will be modified by the two parameters that you see in this inner product here, by v, that is called quite often visibility. So v will be a shrinking factor. We'll just compress, we'll dump this probability in the interference pattern, the oscillations in probabilities. So when v is equal to 1, then we have full oscillations from 1 to 0. And when v is equal to 0, like in this case, we squeeze the whole thing. So effectively, we just go to a flat curve, which is centered here on half, as you could see here. So that's the visibility, the role of the visibility factor, the modulus of this term here. And the alpha term, this corresponds to the shift of this interference pattern. So that's relatively easy to figure out. So figure this out for yourself, and then you can see this beautiful illustration of the trade-off between entanglement and interference. So that will be our problem in the future, right? So we will have our quantum computer. It will be not just a single qubit, but more complicated quantum interference. And the environment is sort of getting entangled with this computer, and then we just lose quantum interference. And then we lose computational power that we want to achieve. So that's kind of a bad scenario. But you know, there are also good sort of aspects of quantum entanglement, and we will talk about them later on.